Hi guys, in this video I would be talking about carbohydrates. Basically when we talk about carbohydrates, we call it as saccharides. It could be actually distributed into three zones. First zone is of monosaccharide. When we say monosaccharide, then what comes to our mind is glucose or fructose. Then comes disaccharide. When we say disaccharide, what comes to our mind is sugar that we consume every day. Alright, this sugar has got glucose and fructose combined. And then the third section which comes in is polysaccharide. Polysaccharide is what? And best example is rice. Alright, rice is a polysaccharide of glucose. It's glucose. That is polymer of glucose. This is the structure of glucose. This is D plus glucose. This is L minus glucose. Now, if we observe keenly this molecule, we will find that second, third, fourth and fifth carbon atoms are chiral. I already had explained earlier that when four different groups attach to carbon, that makes it chiral. Now, when we let's check out this second carbon, CHO, OH, H and this. So four groups attached to this carbon are different, so that makes it chiral. Identically, we can also prove that third, fourth and fifth carbon atoms are also chiral. So glucose has four chiral carbon atoms, hence we call it as diastereomers. Alright, now let's understand this positive and negative, which actually we have already understood. This result we get it from polarimeter. Now this glucose, when we place it in polarimeter, we find that it turns the plane polarized light towards left. Now since the plane polarized light is turned towards left, we call it as levorotatory, or symbol wise we put it as minus, whereas this is the counter of this. Now so this, if we place this in polarimeter, we would find that this would turn plane polarized light towards right. So we assign it as positive, or we call it as dextrorotatory. Alright, now this capital L and D are actually old time configuration. Now that's based on glyceraldehyde. In short, what I would say is that penultimate carbon to this OH, when it is towards left, the OH when it's towards left, we call it as capital L, and when it is towards right, we call it as capital D. Now another thing, if we place mirror in front of them, we would find that if we call this as an object, this is the mirror image of that. So that's what is the proof for isomers. Okay, so these two are diastereomers of each other if we just draw a mirror from here. Alright, so now after this, now let us understand how many isomers are possible for this monosaccharide. Now this monosaccharide has four chiral centers. The formula says 2 raised to n, where n is number of chiral carbons. Alright, so 4, so that comes to 16. So this monosaccharide would have 16 optical isomers. Alright, and out of those 16 isomers, these are the two, and out of these two, it's only this one which is significant for all biological purpose. Alright, so it is very much essential for us to know the configuration of all four carbon atoms. Now we have got to understand chirality of glucose. Now it is a bit complex, so prior to getting into glucose directly, Mridula is going to explain simple way of understanding R and S optical isomers. Alright, so let's understand what is R and S isomers, optical isomers, with a simple molecule having one chiral center, and then let's apply it to glucose.
The compound which we have considered is 1-aminoethanol. Here the carbon is attached to hydrogen CH3, OH and NH2, that is A, B, C and D. Since all the 4 groups are different, the compound is chiral. Moving on to the structure of the compound. Here, the carbon is attached to OH, NH2, H and CH3. For your clarity, this is the 3-dimensional structure of the compound. Here, this is the NH2, hydrogen, CH3 and OH. Moving on to the mirror image, since there is a change in its structure, this will be the CH3, hydrogen, NH2 and OH. We are now going to study R&S isomers in terms of Kahn-Ingold Prelog system, also abbreviated as CIP. Here, as I had mentioned earlier, the molecule which we have considered is 1-amino-ethanol. This is its structural formula. As I had mentioned in the 3-dimensional structure, this is that CH3 which is above the plane of the paper, OH and NH2 on the plane of the paper, while hydrogen behind the plane of the paper. This is the atomic number of hydrogen 1, carbon 6, nitrogen 7 and oxygen 8. Here we can see that oxygen has the highest atomic number, so we call it as large L or 1. Moving on, carbon is the element with least atomic number, so we call it as small or S, 3. Now nitrogen is in the middle, so we call it as medium or 2. On drawing an arrow from 1 to 3, LMS, as the arrow is moving in clockwise direction rather towards the right, we call it as rectus or R. Moving on to the mirror image, here we can see that there is a change in the position of NH2 and CH3. Now on drawing an arrow from 1 to 3 or L, M and S, as the arrow is moving in anti-clockwise direction towards the left, we call it as sinister or S.
Having understood the concept of R&S configuration, let's try to apply it to D plus glucose. Alright. Now, first of all, what Mridula explained was with one chiral center, but here we find that there are 4 chiral centers. So since there are 4 chiral centers, so we call it as diastereomer. I explained it earlier. Alright. Now let's see it with carbon 1. When we apply to carbon 1, it's not applicable as it has got 3 groups only attached. Alright. But when we come to carbon 2, we find that it has got 4 different groups attached to it, owing to which we expect chirality. And as per LMS rule, Kahn-Ingold Prelog system, or 1, 2, 3, we would find that here the direction of arrow would be towards the right, and hence we would call it as R. Here when we see, we would see this also is chiral. Why? Because it has also 4 different groups attached to it. So this also is a chiral center. So here we find that the direction of arrow is towards left. And again here as well as here, we would find the direction of arrow. When I say direction of arrow, I mean LMS or 1, 2, 3 is towards right, Hence the configuration of D plus glucose would be 2R, 3S, 4R and 5R. Having understood the structure of glucose, now let us get into the next mission, that is anomers. Let us find out what are anomers of glucose. Alright, this leads to further complication. Alright, let's get into it. What we are going to talk about is Haworth's cyclic structure. Alright, now what happens is when we observe this glucose, this is an open chain structure, that is Fisher's open chain structure. The hydroxide OH, which is present on 5th carbon, does a nucleophilic attack on this carbon of carbonyl group. Alright, and what happens is as this does a nucleophilic attack on this carbon, this pi bond goes above oxygen, generating O minus. Alright, as it generates O minus, then what it does is it takes this proton there, rendering this structure. Alright, so now what has happened? See, a cyclized structure has formed. Alright, now this cyclized structure which has formed is how many membered? It's 6 membered. 1, 2, 3, 4, 5 and 6. Alright, 6 membered ring it has formed. All right. So now, and what has happened is this hydrogen which was over here has taken place over here. All right. Now this carbon where this O has done its attack is known as anomeric carbon, and this OH is known as anomeric hydroxide. All right. So basically, so this is the structure on cyclization. So this is Haworth's structure. Now in Haworth's structure, what we find is anomeric carbon and anomeric hydroxide. So earlier it was an aldehyde group, but now it has become an alcohol group. All right. Earlier this carbon was not chiral, but now this carbon has become a chiral center too. All right. So complication was there with configuration of 4 carbon. Now one more configuration has been added up to that. All right. So another aspect, now that's not all. Another aspect is this OH which is there, you just check out the direction. Now in this case we find that this OH is over here, all right, closer to this O, whereas this OH is away from this O. All right, now this also I'll just show you in next pic how it makes a difference. So now what we find is we have 2 structures now. Okay, now this ring is actually pyrene ring. All right, this ring where 5 carbon involved with 1 oxygen is a pyrene ring. Okay, so this is pyrene ring, this is pyrene ring. But what's the difference between 2? Now you will, as I mentioned, now in this case we'll find this OH is very close to O. All right, whereas this OH is away from O. One which is closer to O, one OH which is closer to O, we call that as beta, whereas one where this OH is away from O, we call it as alpha. So earlier we saw what was that plus minus, then we saw L, and earlier we saw what was this plus and minus. We also saw what was D and capital L. Now addition to that, we also have got to talk about alpha and beta. But mind you, this L and D were of 2 diastereomers, but alpha and beta is of same diastereomer, right? So D itself has beta and D itself has alpha. So you have got these 2 configurations, and these are known as anomers. Another interesting thing is if we have pure this, and if we take its rotation, specific rotation at 20 degree and D line light, its rotation would be plus 18.7. And if we take rotation of this, it would be plus 112 degree. All right. So see, again further differentiation. So alpha beta also has difference in them, difference in rotation. All right. Now, but if we dissolve in water, all right, if we dissolve both of them in water, actual rotation would be plus 52.5. So this gets increased to this get decreased to this. Now this property is known as mutarotation. All right, mutarotation. All right, so these are all the complexities that we have with glucose, monosaccharide. So are we taking care of all these things? Now when I say this has got this rotation, that has got this rotation, that itself means properties also of these alpha and beta are different. Properties of also this L and D are different. All right, so these are also to be considered when we are talking about glucose, when we are talking about supplement, when we are talking about carb. Now this actually is just as an evidence for alpha and beta hydroxy behaving in a different way. Alright, now see, these are all glucose. Now this is your alpha hydroxy, alpha hydroxy, alpha hydroxy. Alright, now this alpha hydroxy then combines with hydroxy of fourth carbon of next glucose. All right, 1,4. So we call it as alpha 1,4 glycosidic linkage. That linkage, if it would have been in a straight chain, we would have called it as etheric linkage, ether. All right, but here, since it is glucose which is involved, we call it as glycosidic linkages. Now see, this is alpha. All right, all alpha linkages with fourth carbon hydroxide of next to glucose. Similarly, we see it here. Now this is found in rice. Now if further again there's a cross linkage, then that is rice, but this is that starch which we get from rice. All right, and this is called as amylose. Now this pic I have taken from 12th textbook. All right, so this is about alpha. Now let's understand what happens if instead of alpha the next glucose is linked with beta hydroxy of glucose. This pic also has been picked up from 12th textbook. Now here what we are interested in is beta hydroxy. We know beta hydroxy, I had explained that this OH, when it's closer to this O, we call it as beta. Now this beta hydroxy is linked with another glucose molecule, and with which carbon? It's with fourth carbon. Hydroxy of fourth carbon is linked with that. So we call this as beta glycosidic linkage. All right, so we have got, it's a polymer, 1 unit, 2 unit, 3 unit, and multiple units linked like that. We call it as a polymer, and this polymer that we get is known as cellulose. Now the interesting part about alpha linkage, which we saw, alpha 1,4 linkage in case of amylose, that is the starch that we get from rice, and beta 1,4 glycosidic linkage here, which we get in cellulose. Now cellulose is not digestible by human, whereas amylose is digestible by human. So see the difference between alpha and beta. It's just same glucose, but in the earlier case we saw it was alpha linkage, whereas in this case we saw it as beta linkage. All right, so that's the difference between alpha and beta. So composition of alpha and beta in carb that we take also makes a difference. Let's understand activity of liver and pancreas with glucose. All right, now liver, this is what is liver, this is what is pancreas, this part is duodenum. You can see this gallbladder which is opening out in duodenum, and even here pancreas is throwing its ingredients here along with gallbladder. Now pancreas, which has got exocrine gland and endocrine gland. Okay, now exocrine, I hope you know the difference between exocrine and endocrine glands. Whatever hormones, juices, whatever they are giving out is directly pushed into blood. All right, whereas in case of exocrine gland, it passes via duct. Okay, systematically passes via duct. All right, so that's the difference between exocrine and endocrine. Now in endocrine we have islets of Langerhans, islets. All right, and these which are there, which you would find here attached here, these are all exocrine gland. All right, now they are called as acini. All right, these secretes all digestive juices. All right, so right now we are not concerned with digestion, we are concerned with glucose. All right, so for glucose endocrine glands are involved. Now endocrine gland is pancreatic, islets of Langerhans. All right, Now islets of Langerhans have alpha cells, which gives out glucagon, beta cells, which gives out insulin, delta cells, which gives somatostatin. Alright, these are all there to maintain glucose homeostasis in blood, maintain glucose level in blood. Just in short, I have just mentioned here. So what does alpha cell do? Gives out glucagon. What does glucagon do? It increases blood glucose level by stimulating liver to break down glycogen. Glucose is stored in form of glycogen in liver. Glucose stored as glycogen in liver. So glycogen to be released in blood as glucose. It also activates glucogenesis, converting amino acid to glucose. Now this happens when you are fasting, when your supply of glucose has decreased. At that time what happens? It is like glucagon only which is responsible for synthesis of glucose from amino acid. Alright, then that's all about alpha cells. Now what does beta cell do? Beta cell gives out insulin. Insulin, what? It transports sugar or glucose to liver, muscles and tissues to be stored as glycogen. So beta cells or insulin, it from blood it would pass glucose to liver to be stored in format of glycogen. All right, so what's the job of delta cell? Delta cell gives out somatostatin. Now somatostatin regulates pancreatic endocrine function, so it's the boss which controls both of them. All right, so this is how glucose homeostasis is maintained in blood. So it is collaboration of pancreas with liver. Metabolism of glucose occurs in cell. Here I have just considered mitochondria and cytoplasm or cytosol. Alright, and it occurs in two steps. First is glucose getting converted to pyruvate and to energy rich adenosine triphosphate. Structure of pyruvate is CH3CO COO minus, and who helps it? It's pyruvate kinase enzyme. Once pyruvate is formed, it is pushed into the powerhouse mitochondria where lots of oxygen is present, which oxidizes pyruvate to carbon dioxide and water plus 36 ATPs. Alright, so it's 36 adenosine triphosphate molecule. So in all, on metabolism of glucose, we get 36 plus 2, that is 38 ATP molecule. There's a bit of discrepancy about this number of ATPs over here, but I have considered it to be 36. Alright, so total 38 ATPs are generated in metabolism of glucose. In incoming section, what I have done is I have just calculated the amount of energy required in terms of ATP for synthesis of carbohydrate, and at the same time also this happens in plant, and also when we consume carbohydrate or D-glucose, say D-glucose, when we consume D-glucose, now how much ATP or energy is generated. So I just have drawn a profile, it's quite interesting, just view it and then let's move further. Here I am just trying to present a profile of energy required for synthesis of glucose to energy given out while glucose is being metabolized, alright, in our body. Now glucose synthesis consumes 18 ATP per molecule. Alright, so that's the energy of reactant. Now once it is formed, it directly doesn't get converted, it doesn't get metabolized by itself. It has to pass via an uphill. Now this uphill is known as activation energy. Alright, now the activation energy can be reduced provided we have catalyst, and we have seen we have pyruvate kinase, and then again in mitochondria we have varieties of catalyst which works in for lowering this uphill. Alright, so basically what happens is glucose gets converted into carbon dioxide, water, and also ATP. So we are concerned with ATP here because as it's an energy profile. So while metabolism of glucose, 38 ATP molecules are generated. Alright, 18 consumed, 38 generated. So this becomes an exothermic process where energy is given out. Alright, now you may be wondering, from where does that energy come? Like when glucose is being broken down, from where does it come? Every bond which has got energy entrapped in it. Like I have just given you a table over here where CH bond, like if you take this CH bond, CH bond, CH bond, CH bond, each bond renders 418 kilojoule. Alright, similarly CC bond, now say CC bond, these are CC bond, this gives 348 kilojoule. C double bond O gives out 799, so on and so forth, right? So that's how we get energy. When all bonds are being broken, we get relevant energy for relevant bond. All right, now we always talk in terms of ATP. It is an energy rich molecule. So I just have tried to explain a bit about ATP also, and how do we get energy when ATP gets converted to ADP and AMP. All right, this is the structure of adenosine triphosphate, which has one nitrogen base known as adenine and one ribose sugar which is of 5 carbon, and along with it, it also has 3 phosphate groups. All right, so that's why we call it as adenosine triphosphate. Adenosine, why? Adenosine means when nitrogen base is attached to sugar, ribose sugar, it is called as adenosine. Otherwise, this is known as adenine. So adenosine triphosphate. All right, now what happens is, suppose this ATP hydrolyzes and liberates one phosphate. So what happens? ATP gives you ADP, adenosine diphosphate plus inorganic phosphate, plus it gives this energy 7.5 kilocal per mole, or in terms of joule it would be 30.5 kilojoule per mole. Now that's the energy which it liberates along with one inorganic phosphate. Now if same ATP gets converted to AMP, adenosine monophosphate, then what happens is ATP gives you AMP plus 2 inorganic phosphate plus double this energy. All right, so that's the reason why we call it as energy rich molecule. So ATP is energy rich molecule owing to this reason. Main contention of this video was to make everyone aware about carb or D-glucose. All right, now my next video would be on carb as a supplement being used by guys, those who work out. Okay guys, see you then.